In this video, we're going to define the definite integral. So remember from last time, I talked about it as area, but actually it's signed area, which we're going to talk about in a minute. So we want the area under a curve. We're approximating it using n rectangles. Okay, then if you take the sum of these areas of rectangles, as the number of rectangles goes to infinity, this area approaches the actual area under the curve. Okay, so what we had in the last video is we approximate the area with a sum from the first rectangle to the nth rectangle, where each one has area delta x times f of xk. Okay, so this is the width of each rectangle, and this is the y value, okay, at some choice within the interval xk, and this is what we use for the height of the rectangle. Okay, so the height of these things is what's changing. We're using equal sized width each time. You don't actually have to use equal sized width, so you can make this more general, but we don't need to because we just want the basic idea so that we understand what the definite integral is doing. So then the actual area would be equal to this as we let the limit, the number of rectangles, go to infinity. So if I take the limit as n goes to infinity of this sum, then I get the actual area under the curve. Okay, now I should be careful about saying that because it's not really the area, it's the signed area. So I'm going to give you a picture down below to sort of emphasize this. But this is what we're going to define the definite integral to be. So if f is defined on an interval from a to b, closed interval, the definite integral of f from a to b is given by, so we use this notation. So it's our integral symbol with an a on the bottom and a b on the top, and it's f of x dx. Okay, so it looks very similar to our indefinite integral. Okay, this is going to be equal to this limit of this sum. Okay, we're not always going to use it like this. Like I said in the last video, we're not actually going to be computing the limits of these sums. Okay, they're kind of tedious to do. Not that they're challenging, but they just take some, you have to be pretty good at algebraic manipulations. So this a we call the lower limit. Okay, and this b we call the upper limit. Okay, and then here, so this is obviously provided this limit exists, which we know it doesn't have to always exist. Delta x is always the width of the interval. Okay, so that's the total width of the interval divided into n parts. Okay, and xk is any x value from the case interval. Okay, so that's what we're using for our y value. So here's where I want to talk about how this relates to area. So we were using the idea of area to rely on your intuition, so why this is what it is. But it actually only represents the area under the curve, above under f of x, above the x-axis, and between x equals a and x equals b, only if the function f of x is positive on the interval. Okay, so this means that i.e. f of x lies above the x-axis, or touching. Okay, if our function goes below, so maybe I'll just do a little picture here. Okay, so if f of x, so like it did in our previous example, if it looks something like this, and my a is here and my b is here, okay, then this is going to be the area. Okay, so if I call that a is going to equal the definite integral from a to b of f of x dx. Okay, because f of x is entirely positive. Okay, but if I have some picture that looks like this, okay, and maybe a is from here, and maybe b is over here, then the area that I'm talking about is going to be this part, but also this part. Okay, now using our method, if we break up into rectangles, okay, something like this, the ones in this part below, so maybe there's a little line here and then, okay, these ones are going to have a y value that's negative. Okay, so something like this. Okay, so here, f of xk, so the y value, is going to be less than 0 in this part. So that means that the area of that rectangle is going to be negative, because it's d of x times f of xk. So we're sort of allowing the area to be negative there. Okay, so since area should always be positive, each rectangle should have positive area. In order to determine or approximate the area under the curve. Okay, but this doesn't happen if f of x is ever negative. Somewhere in the interval from a to b. Okay, so that's why we call this thing, the definite integral, the signed area. So what I mean by that is under the x-axis counts as negative area. Okay, so if they ask for the definite integral, this thing could be negative. Okay, if more of the area is underneath the x-axis, then this will be a negative number. Okay, it could also be 0 if the same amount is above and below. If they ask for the area, then we have to be more careful. Okay, so we're going to do some examples of that at some point. So if they ask for the area, we need to be careful to make sure that we count these negative portions as positive. Okay, so that's what's going on here. So let's do an example. So suppose I want to approximate this definite integral using 4 rectangles, okay, with equal width. That's what we normally do, and we're going to use the left endpoint, okay, just because. So let's just draw a picture. Okay, we should know what this one looks like, maybe. So it's just a square root that's been shifted 1 unit to the right. Okay, so my graph is going to be at 1, and then it just rises like the square root graph. Okay, so like that. So we're going from 1, 2, 3, 4, and 5 to 5. Okay, now our delta x is going to be b minus a, so that's 5 minus 1 over 4, because we want to use 4 rectangles. So that's 4 over 4, so that's 1. So each of the rectangles have width 1. Okay, so if we were going to draw them, these are going to be where they split at all the integers. Okay, now because we're using the left endpoint, the rectangles, so this is going to be my y value in the first one. In the second one, this is going to be my y value. The third one, this is my y value. So I'm always using the x coordinate on the left of the endpoint. Or sorry, the left endpoint of each interval. So that's the area I'm going to use. Okay, that's what it looks like. So the definite integral from 1 to 5 of square root x minus 1 dx is approximately, okay, so if we're going to use the sum notation, it would be the sum from k equals 1 to 4, because I'm using 4 rectangles. Delta x is 1, okay, and then it's the square root of xk minus 1, okay, whatever our endpoint is. Okay, so this is going to be 1 times square root of 1 minus 1 plus 1 times the square root of 2 minus 1. Okay, so that's our endpoint 2. Plus 1 times the square root of 3 minus 1 plus 1 times the square root of 4 minus 1. Okay, so this is 1 times 0 plus 1 times root of 1, so 1, plus 1 times root of 2, plus 1 times root of 3. So 0, so we get 1 plus root 2 plus root 3. Okay, which is approximately 4.1463. Okay, so that would be our approximation of the area here, using 4 rectangles. Okay, so this is the type of question you should expect. Okay, where I give you a function and I tell you how many rectangles and which endpoint to use. So let's try another thing. So suppose f of x is x squared plus 20. This gives the rate in milliliters per hour that medicine is given to a patient X hours after their IV is connected. Okay, so it's giving you the rate. That's important. So, at what rate is the medicine flowing 2 hours after the IV is connected? Okay, so this is after 2 hours and we want the rate. Well, that's exactly what f gives us. So this is actually just f of 2. So that's going to be 2 squared plus 20. So that's 4 plus 20, so 24, and the units are going to be milliliters per hour. Okay, after 3 hours, it's just f of 3, so it's going to be 3 squared plus 20, so that's 29 milliliters per hour. Is this flow rate constant? Okay, so no, obviously not. F of 2 and F of 3 are different. So in the after 2 hours, the rate is 24 milliliters per hour, but after 3 hours, it's 29 milliliters. So no, obviously not. F of 3 is bigger than F of 2. Okay, so what that means is the rate changed. So it's not constant. So what if we wanted to know the total amount of medicine given to the patient between the 2nd and 3rd hour that their IV was connected? Okay, so if the rate was constant, okay, let's say it's constant at the F of 2 rate. Okay, then it would be easy. So then we would know the patient got, so if the rate is 24 milliliters per hour and we're doing it between the 2nd and 3rd hour, so for 1 hour, we would know the patient got 24 milliliters exactly in that hour. Okay, but what's actually happening, this is an approximation. So our function, we actually know what this function looks like. It's a parabola that opens up. So at 0, it's at 20. And then at 2, it's at 24. And at 3, it's at 29. So what we just did is we use a left endpoint in one rectangle. The area here, the amount of medicine, is 24 milliliters. So we did the rate times the width of this rectangle. So we just approximated it, okay? But ours is not constant. So this would be, we know that it's going to be an underestimate because the rate is increasing and we use the smaller rate. It's an underestimate. We could do the overestimate. So if we use the right endpoint, then we're going to have 29 milliliters. So we know that the amount that they actually get in that time is more than 24 milliliters, but less than 29 milliliters. Okay, just by doing this approximation. So let's try and get a better approximation. So let's do this using 4 rectangles, okay, instead of just 1. So we're going to have the same picture. I'm going to make it a bit bigger. Okay, so it looks like that. So here's 2, and maybe here's 3. So I want to split this into 4 bits. Okay, so delta x is going to be 3 minus 2 over 4, so 1 over 4. So every 1 over 4, I'm going to have to split. I didn't do that very well. Maybe I should fix it a bit. Okay, so let's do it in half. Okay, and then each one of those in half. It's a bit better, but so this is going to be 2.25, 2.5, and 2.75. Okay, so we're going up by 0.25 each time. Okay, now let's do this maybe with the left endpoint. So if we're using the left endpoint, my rectangles are going to look like this. Okay, so then using the left endpoints, I'm going to have the amount given, okay, between the 2nd and 3rd hour is approximately, I should use, okay, so dx, which is 1/4, times the y value, so this is going to be f of 2, plus 1/4 f of 2.25, plus 1/4 f of 2.5, plus 1/4 f of 2.75. Okay, so if I compute this, it's 1/4 times 24, plus 1/4 times 25.063, plus 1/4 times 26.25, plus 1/4 times 27.563. So I get a value of 25.72 milliliters. Okay, and again, we think that this is probably an underestimate because it looks like we have some missing area. I'm going to do this in a different color, in green. Okay, so it looks like that we're missing this little bits here. Okay, so we didn't get all the area. So we definitely have an underestimate here. But it's probably closer to the actual value than 24 milliliters. Okay, if you wanted an overestimate, we could also use the right endpoint. And then the amount would be approximately, so we'd have 1/4 f, so we don't use f of 2 first, we use f of 2.25, and then 2.5, and then 2.75, and then our last one is actually f of 3. Okay, if you do this, then you should get 26.97 milliliters. So now we know, okay, and if I use the right endpoint, I'm going to get an overestimate. Okay, so now instead of between 24 and 29, we know that the amount is between 25.72 and 26.97. Okay, if we use more rectangles, we could even get it closer. Okay, now if we let the number of rectangles go to infinity, we get the actual amount of medicine in that time. Okay, now because I said we're not going to actually compute those limits, we're going to need a different way to find these. So in the next video, we're going to see how we would go about finding those. And then we'll compute the actual number here. So try to remember these numbers so we can compare. I'll remind you in the next video though. So more generally though, this is the total change, right? So what we're actually looking for is, so little f of x gives us the rate that the medicine is being administered. But what we actually want to know is how much medicine after 3 hours, or how much medicine after 2 hours. So if we had the amount of medicine they gave and we took the derivative, that's going to be the rate that we give the medicine. So the amount is actually the antiderivative. So this is the idea behind a total change. So if you know the rate, so if they give you a rate of change, okay, of some function capital F of x in some interval, then the total change in f of x as x goes from a to b, well, this is just capital F of b minus capital F of a. Okay, but it's also going to be the area under the curve of the rate. Okay, so this is, oh shoot, sorry. I wanted to actually do this differently. So the total change is the definite integral. So it's the definite integral from a to b of the rate function. Okay, and this is going to be the area under the curve, which is the limit as n goes to infinity of our sum of our area rectangles. Xk. Okay, but if we knew capital F of x, then we know it should be f of b minus f of a. Okay, and this is the idea behind what we're going to call the fundamental theorem of calculus. Okay, but we're going to talk about that in the next video.